So next, for this afternoon, we have Christopher Key. Is it Keys? Am I saying that correctly?
That's right.
Okay, at Emory, and he'll be speaking about an upper bound for the number of arithmetical structures on a graph.
Great. Oh, thanks so much. And thanks for getting my last name. You'd be surprised how many people don't get it and don't ask. So I appreciate that. Yeah, thanks for having me. This is actually my first talk at a virtual math conference. I've been really looking forward to this. So I'm excited to see how it goes. Hopefully it's good. All right, so today I'm going to be talking about some joint work that I did with my colleague Tomer Reiter on counting arithmetical structures on graphs. So you can find our paper at the archive, and there's a link in my slides. Hopefully I shared them in the chat. Maybe the hosts can help me, can copy it again just in case someone came in later. But so today what I want to do is start by first defining the objects. I'm going to say what arithmetical structures are and draw lots of pretty pictures to give some examples. And then I'm going to describe a construction that Tomer and I came up with, which associates to an arithmetical structure on a graph G, whatever that means, to another arithmetical structure on a smaller graph. I really should say smaller in quotes here. I just mean a graph with one fewer vertex. And again, I'll draw lots of pictures for everybody here. And then the next thing will be to present our result that we get from this, which is as follows. So the theorem is if we have G, a graph, which is connected, undirected, with n vertices, and no loops, but possibly multiple edges, then we have an upper bound for the number of arithmetical structures that could be on G. And it looks like this. All right, so you'll see this again, and we'll talk about sort of where these pieces come from, and hopefully I'll be able to give you enough of a kernel of how the proof goes that maybe you'll be interested. In particular, the new feature of this bound is that we're saying very little about the graph G. In other works about arithmetical structures, they say things, but only about very specific cases of graphs. So even though the bound is kind of ugly, it is saying something new. And then time permitting, which I think it'll be close, I'd like to say just a couple of things about the specific case where G is a complete graph. Okay. So let's just start with some setup and notation. G is going to be, like I said, connected, undirected, and we're going to always let n denote the number of vertices, and we'll use E of G to denote the edge set. And I'm going to assume the vertices come with an ordering v1 through vn. And then I'm just going to use A and these delta ij's for the adjacency matrix and the number of edges between two vertices. And then again, like I mentioned earlier, G is going to have no loops. Now, the hypothesis that G has no loops isn't really that interesting. It just happens to be very natural in the setting that arithmetical structures come from. And the same with connectedness. It's really changing those hypotheses wouldn't be that difficult, but it also wouldn't be very interesting. So let's define what an arithmetical structure is. So given a graph G, an arithmetical structure is the data of two n-tuples, which I'm going to call R and D, that satisfy the following system of equations. Right? A more compact way of writing this that I like is that Ri for any fixed I divides the sum over indices j not equal to I of delta ij times Rj. Okay, so here the d values are implicit, but you could, of course, come up with what the d value is by, well, that means divides means exactly that there is some d for which Ri equals this side. And so oftentimes I'll just write an arithmetical structure as the data of R. And we need one more thing to define an arithmetical structure. We need this R vector to be primitive. So we want the GCD of all these integers in the R vector to be equal to 1. All right. And often it's convenient to write D, capital D, as the diagonal matrix coming from this vector D, in which case we have R is described as in the kernel of D minus A. So arithmetical structures arose back in the 80s, actually, the late 80s, when Lorenzini introduced them to study special fibers of proper minimal models of curves. I don't want to say too much. I do not consider myself an expert on this. But what I can say is that in that context, the graph G is the dual graph of the special fiber. And these R and D values come from studying the intersection pairing on the model with the special fiber irreducible components. So if you want to learn more, I encourage you to check out some of his papers. So let's see some examples, and I want to draw some pictures. But first, in a sense, the most boring and interesting example, we could just take all these R values to be equal to 1, in which case the D values are the degrees of the vertices. And this actually has been given a special name. The matrix D minus A is also called the Laplacian. So if you've heard of a graph Laplacian, then this is what it is. It's just an arithmetical structure. So I say it's boring only because the R values are equal to 1, but these graph Laplacians are actually quite interesting. And there's been a lot of research done on them. One thing that people like to study is the critical group, which is the torsion part of the co-kernel of this matrix. You can similarly define a critical group for arithmetical structures, but that's not going to be the focus of my talk today. So let's now give some more interesting examples, again, in the sense that the R values are not all 1. So here's one. It's just a path with 3 vertices, and we've got an R value of 2 in the middle. So if you're nervous, Chris, why is this an arithmetical structure? Well, let's just check. Does 1 divide that sum that we wrote in the previous slide? Well, always it does, because 1 is 1. 1 divides everything. Then we can check that 2, right? 2 times 1 is equal to 1 times 1 plus 1 times 1. So I've just written something very obvious, but this is the data of checking that 2, so I guess if I scroll back, we're checking that this equation is satisfied at the vertex where R equals 2. Okay. All right. Things can get a little more complicated. Here's a simple graph, and you can go ahead and check at these vertices that the hypotheses are satisfied. And of course, the tuple with all these integers in it is going to be relatively prime, or I guess not pairwise, but the GCD of the whole thing will be 1. And then we can have examples which aren't simple graphs. Remember I said we could have multiple edges. So here's a graph which almost looks like K3, a complete graph on 3 vertices, but each edge is doubled. And we can have an arithmetical structure on here as well. Okay. So these will all actually come back later, but we have a pretty picture just to engage your eyeballs a bit. Are there any questions here about the definition that anyone wants to ask now? Okay. All right. So my title had, I think, counting or maybe bounding. I don't remember. But let's let AG denote the set of arithmetical structures on our graph G. So G is fixed. And here's my question. For a given graph, how large is this set? So how many arithmetical structures exist for a given graph G? What do we know? Well, for a long time, we knew not much. So Lorenzini proved that the set of arithmetical structures is finite. So only finitely many of these things on any given graph. And it wasn't until pretty recently that these other results came. But a couple years ago, a large group of mathematicians proved that for a path, so a path with n vertices, right? There's a path. The number of arithmetical structures can be described combinatorially as a Catalan number. If you're not familiar with Catalan numbers, like I'm not, these have an expression as a binomial coefficient. So that's pretty cool. This for a very specific structure of graph, we have a very explicit, just an exact count of this number of arithmetical structures. And similarly for cycles with n vertices, so a regular polygon, there's a really poorly drawn C4, we have a similar count in terms of Catalan numbers. Moving beyond that, there have been a few recent papers about bidance. So if I don't know, was more tactful, I could come up with a political joke. Paths with doubled edges. And people have studied recently how many arithmetical structures are on these things. But so far, the results aren't exact counts anymore. Like in the previous cases, they're upper bounds or possibly asymptotics or conjectures. So even with these small perturbations in the graph, we can't get that complete information that we can for paths and cycles. Okay. So Tomer and I noticed that the graphs that had been studied have a lot of regularity. And that regularity, right, the path is very rigid, had been used and exploited to give these counts or these bounds. And what we wondered is, what about a general graph when we know absolutely nothing? Could we come up with a count or a bound or something for the number of arithmetical structures when all we know is the number of vertices and the number of edges of our graph? And the answer is yes. Yes, we can. Here it is. All right, so this is the result I mentioned earlier. Now it's pretty bad looking still. It's factorial in the number of edges, and then it's got the edge set as a base, and the edge set is also in this exponent. There's some logs over here. There's a 2 to the n showing up in a few places. This thing is, in one sense, terrible because it grows so quickly with respect to both the edge set and n. But on the other hand, it's better than nothing, which is what we know we had before for the general case.
How does it compare to the Catalan number bound from the special case earlier?
Well, yeah, great. So if n is, okay, so if we have a path, say, in the case of Pn, this EG would be equal to n minus 1. So we'd be looking at n factorial times n to some nasty power, also including n. This is way, way worse. So yeah, that's a great question. And it brings up the point that this general bound has to be worse because it takes into account no information about the graph. And I don't think we should expect it to do anywhere near as good as those counts do in those cases. Yeah. So really quick, let's just give a rough sketch of the proof. The idea is we start with an arithmetical structure on G with n vertices. And Tamara and I cook up an arithmetical structure, which I'll call R prime and D prime, on some graph G prime with n minus 1 vertices. So this is this key construction that we came up with that we use in the proof by induction. Okay, so I'm not actually proving anything. This is actually a fair bit of work. And then once we use induction, we reduce it to the case where we have a graph with 2 vertices. Now, in the graph with only 2 vertices and many edges, we actually have a really nice explanation. So I call these banana graphs because I think they look like a banana. So here's a graph with 2 vertices and 3 edges. Looks kind of like a banana. I can't get it out of my head. These are now known to me as banana graphs. So I'm going to use sigma 0 of n to denote the number, the divisor function. So the number of positive divisors. I don't want to overload d. It already has another meaning. And what we can prove is actually that the number of arithmetical structures on our graph is the same as the number of divisors of m squared, or number of edges squared. And there's a really neat quick proof. So if you just write down what it means for R and D to be an arithmetical structure, what you're really talking about is the data of a co-prime pair of integers, R1 and R2, such that R1 divides MR2 and the symmetric relation, R2 divides MR1. And notice that this implies, since these are co-prime, that R1 must divide M, and so must R2. So we have this set now of co-prime pairs of divisors of M. That's what it means to be an arithmetical structure. And there's an explicit bijection that you can write down. This isn't easy, or this isn't hard to prove. It's a bijection where we send R1 and R2 to MR2 divided by R1. Remember, R1 is a divisor of M. Okay, so we can pretty easily prove that in the case of graphs with only 2 vertices, we do have an exact count, and it's purely number theoretic. I should point out here that the divisor function is super irregular, right? We know that the lim int of sigma 0 of a square is 3, right? A prime squared has only 3 divisors, 1, the prime, and the prime squared itself. So this thing, as m grows, is fluctuating a ton. And this is where we get that nasty, well, I'll show you again when it comes up, but we get that nasty factor on the right side with a bunch of logs in it. That's us taking a monotonically increasing upper bound for a divisor function. That's where that part comes from. Okay, so with my remaining time, I just want to draw some more pictures for you and showcase the construction we came up with. That's the key idea in our induction step. So we can get down to graphs with 2 vertices, our bananas. So I'm just going to show you how the construction works by giving examples directly. All right. So if we start by with an arithmetical structure, RD, we're going to just remove a vertex. We're going to just remove V1 for simplicity and construct a graph G prime from the remaining vertices. So we remove that first vertex and all the incident edges, and we're going to replace the remaining edges by D1 copies. So this part of the construction really depends on which arithmetical structure we start with. And I think this was the step that sets it apart from other similar constructions found in the literature. For the remaining distinct vertices, we add back in edges. So I think of this as we're adding back in edges that we took away before if they passed through V1. And we obtain our arithmetical structure R prime by simply deleting R1, so deleting that first entry, and then rescaling if necessary, remembering that we want our arithmetical structures to be a primitive n-tuple. So now in pictures, if here's our graph, this is a path P2. Let's say we want to remove the middle vertex. We start by removing all the incident edges. We move to step 2, but there's no remaining edges to replace, so we don't need to. And then for the remaining distinct pair, okay, so for the one pair of edges, or vertices, excuse me, we add back in 1 times 1 edges, right? We're just replacing the path that went through V1, and that gives us our graph G prime. And notice that these R values make an arithmetical structure on this new graph G prime. Now, of course, this is sort of a trivial example. We know Ri equals 1 is always going to be an arithmetical structure. So this is kind of a boring end result. So let's see some more interesting ones. So here we have another graph from earlier, and we want to remove the vertex in red. So let's do that. And now we go back and see that, well, let's calculate what D1 is here. So D1 is going to be equal to 2, because R1 is 2, and these add up to 4. So we're going to replace all the edges that we have on this graph with 2 copies. So now we have a multigraph, but it's disconnected. So we reconnect it with our final step, adding back in sort of these edges between these pairs of vertices. And we have the following new graph, G prime. And you can check. So if you don't want to pay attention to my last minute of speaking, you can go ahead and check me that this is actually an arithmetical structure. So I have one more example, but because I'm really short on time, I'm going to kind of breeze through it. If we had this is a K4, K4, an arithmetical structure on K4. We can reduce it in 2 steps to a graph on 2 vertices, all right, by following this procedure. So I should say that this is kind of a generalization of the process known as smoothing in these papers about paths and cycles. And it turns out that in the case where D1 is 1, this construction is inverse to Lorenzini's blow-up construction. So what that was you start with the graph G, and instead of taking away a vertex, you add a new vertex and build an arithmetical structure on a larger graph. And when D1 is 1, these are actually inverse to each other. So a corollary of this observation is that when D1 is 1, we actually preserve the critical group of our arithmetical structure. And an interesting question that I haven't really thought that much about, but I think would be fun to answer is, can we say anything more about how our transformation affects the critical group in general? Is there a map of critical groups? What's going on when D1 is greater than 1? Okay. So because I'm out of time, I'll spare you the extra detail that I was hoping to give. But if you do an induction here and you keep track carefully of how the edge set is growing each time you do one of these, apply this construction, and then you apply a monotonically increasing upper bound for the divisor function at the end, you get something like this. So hopefully you believe me that it makes sense that the number of vertices would show up as an exponent, and some value of the divisor function would show up here. But I'll leave the rest of the details to my paper. So I'm going to stop there, but I'm happy to answer more questions. So thank you all for your time.
I have a question, Chris.
Sure.
So Dino's blow-up, blow-down construction, which is also an art inventor's, actually corresponds to blowing up a point. If you think of these as dual graphs, correspond to blowing up points.
Right.
is your kind of, can we think of your thing in terms of algebraic geometry and maybe, I mean, you may be working with singular models or something? Is that
Yeah.
a good explanation of your construction?
That's a really good question. And I'd spent a little bit of time thinking about this, but I couldn't come to a definitive conclusion. It seemed to me like there were examples where, and I think this was the case where D1 is 1, you really do have something geometric going on. But in the more general cases, that didn't seem to be true. But I don't have a satisfactory answer for you right now. I would like to say, yes, this comes from something geometric all the time, but I can't tell you what that is. So it might be that I just don't know, or someone out there knows and can help me out and answer your question. Or it might be that there needs to be a modification of this construction. Maybe this is an acceptable answer for this question, but maybe there's a better version of this type of construction that does have more of a geometric underpinning. Sorry, I don't have a better answer for you.
Any other questions for Chris? DZV.
What were you going to say about Egyptian fractions?
Awesome, thank you.
Your plant.
Yeah, so in the case of, there we go. In the case of complete graphs, so we started by thinking about complete graphs, we call it KN, but actually a better, more general thing that we have to think about is this, I call it MKN. I don't know if these have a name. I want to call them multi-complete graphs, but this is what I would call a 2K3. It's just K3, but with 2 edges or instead of 1 between each vertex. If someone knows a name, they should tell me in the chat or something for this. But it turns out that the arithmetical structures on these MKNs are in one-to-one correspondence with primitive solutions to these unit fraction representations of 1 over n. So these are also called Egyptian fractions. And the fun punchline of this part of the paper is that we can actually use work that bounds the number of Egyptian fraction solutions there are to get a bound on the number of arithmetical structures. And that looks like this. So it turns out these are slight asymptotic improvements over our bound, well, a refinement of our bound for the graph MKN. But these don't have explicit constants the same way that our bound does. So, and it's a pretty similar shape. If you look really carefully at these, you can kind of see the shapes are a little bit similar. So you might expect that we can't do too much better with these arithmetical structure bounds without some serious improvements.
Awesome. Any other questions for Chris? Not, let's thank him again.
So thank you all so much.